Okay. In the previous video, I talked about what did I talk about? Histogram linear stretching. So we can represent the intensity of a grayscale image in an histogram form, with 0 being the darkest and 255 being the brightest. That way, we can represent it in the histogram. And if we find that the video or the image is under contrast, we can improve the contrast of the image by linearly stretching out the histogram. So that way we have enough pixels that's in the dark side and enough pixels in the bright side, and that's how we get a better contrast. And this is actually very simple, and this is what Dr. Lee preferred. But today we also talked about another technique called histogram equalization. So I'm going to show you that. Essentially, histogram equalization is looking at the histogram as if it is normally distributed. So think of it as a normally distributed curve. And we want to change this to a uniformly distributed curve. So you take the original image and its histogram, and you want the histogram to be as uniformly distributed as possible. That's what we're trying to do. So in a continuous case, it is possible to do it. What we can do is we can use something called spreading, where we take one bar, actually it's a continuous case, where we take one peak and we try to reduce the intensity of these pixels, and at the valley of another curve, a valley of the same curve, that we raise the intensity. So on intensity levels that are really low, we boost up the intensity. On levels that are really high, such as a local minima on a histogram curve that is continuous, we can reduce the intensity so that we get a flat line, if you think of it in a continuous sense. But images are not continuous. They are actually discrete. So how will we do that? Well, you could think of it as a bar. So some image, say for example, on intensity 100, number of pixels that are on intensity 100, what we could do is we could have some of the intensities spread out to the other side. So such as we could move some intensity to 101 if it's lower than the average, and we could, if on intensity 100, if it's too high, we can just reduce it. But nobody actually do that. What we actually do is we, instead of spreading out the intensity levels, what we actually do is just, if one level is too high, we just simply remove the one right next to it. So some of the terminology I would like to go over is, the first one is N. N back in the days, it stands for the number of pixels from the width of the image. Number of pixels, the width of the image in pixels. So N, for example, will be 1,000. And if this is a square image, it would be 1,000 by 1,000. So N squared would be the number of pixels in the image. And M, I forgot what M is. Oh, right. M is the intensity level. So M is 2 to the 8. So n minus 1 would be the brightest, 255. That would be the brightest image. And 0 would be the darkest image because we are computing science. So n squared, number of pixels, divided by m, which is the number of discrete levels from 0 to 255, that would give us the average pixels, the average intensity for every intensity level. So that tells us, for every pixel, we need to try to put it as close to n squared divided by n as possible. What else? And what we would try to do is we would have a function that we call q, which is actually just, if you think of the histogram curve as a probability density function, and if you calculate the area under the curve, then you can think of it as a cumulative density function, a CDF. So essentially what the cumulative histogram is a integration of you're trying to find the area under the histogram. So that would tell you the number of pixels that is I didn't quite get this. So the mapping from P to Q is defined as a function of Q of P, where P is the intensity level that we want. So if you integrate from 0 to P of I, then that would tell you the area under the histogram. And then that would tell you the number of pixels that are below the brightness level at P of I. Now the function is actually defined by the integration from 0 to P of I, h of P with respect to P. And this is over n squared over m. So then this would be the algorithm for histogram equalization. This is part 1. I'm going to get back to you exactly what we mean when we divide the integrated function by n squared over n. So stay tuned for part 2.